modulation. So digital modulation basically transforms the bit stream into waveforms. These waveforms are used in transmission lines, physical transmission lines, which can be any transmission medium, air, satellites, transmission, and copper wires, physical wires, whatever it is. So the idea of digital modulation is using those bits and transforming those bits, and there can be several modulation schemes to do that. Now some quick terminologies for digital modulation shall follow. So what happens is that to a digital modulator, the output of the channel encoder comes. So it's a digital modulator, and the output of the channel encoder are k bits. So they are k bits. So it's a stream of bits 0, 1, 1, 0, 0, 0, 1, 1, 0, something like that. Now this basic idea is that how many bits are there? K bits are there. So how many symbols can be created out of those bits? There can be n symbols, which is n is equal to 2 to the power k. That means k should be equal to log base 2 of m. Knowing these basic stuffs is very important. So what is the symbol rate? So the digital modulator creates a waveform, that is SMT, based on one symbol m. So for one symbol there is one waveform SMT, and that waveform is transferred. So the time to transfer that waveform is, suppose, the time period t. So the symbol rate shall be Rs is equal to 1 by t. That is the time period to transform one waveform. So the entire time period of that waveform is t. So we have 1 by t as the symbol rate. Then what is the bit rate? So the bit rate is the total number of bits that is transferred by one symbol. So a symbol shall contain k bits. If the symbol contains k bits, so the bit rate should be R is equal to k times Rs, that is k by t bits per second. So that must be the bit rate in the communication. So we have the symbol rate and the bit rate. Okay, va bene, we are done. Now with the terminologies, this SMT, what is this? What is this SMT? So this SMT is some sort of Sn times phi t. What is this phi t? This phi t is a carrier. This phi t is a carrier signal. So phi t can be given by some cosine signal, cos theta. Okay, or let's say more specifically cos 2 pi f naught t. This is a carrier, where f naught is the carrier frequency. So when we are transmitting data in any medium, we are putting the data on a carrier. So the carrier basically carries the data in the transmission medium, and this is the carrier frequency f naught. So phi t is that carrier, and Sn is some value. Now this Sn has a value space. So for k bits, this Sn can take certain amount of values. So all those values that Sn can take, the set of values that Sn can actually take for all the symbols possible, that is m is equal to 1 to capital M, is giving us what we call a constellation diagram. So this is our constellation diagram, the set of values. So for as a whole, two symbols are there. So n is equal to 2. Let's take an example. So there should be how many bits? 1 bit. That means two symbols are essentially 0 and 1. So the Sn will have certain values. So the certain value will be for symbol 0. What is the value of Sn in the constellation map? So suppose in pulse amplitude modulation case, here we shall put the symbol 0 and here we shall put the symbol 1. So this is -1, 0 and this is 1, 0. So Sn is a set of values, the coordinates -1, 0 and the coordinate 1, 0. That is the constellation, support of the constellation, and this diagram we draw is the constellation diagram. In any case, moving forward, we have digital modulation, several schemes. One scheme is pulse amplitude modulation. So we are essentially doing what? We are essentially making SMT is equal to SM times phi t, where phi t is our carrier signal. So the pulse amplitude modulation is based on the idea that SMT is equal to AM times GT cos 2 pi f naught t, where f naught is our carrier frequency, GT is a finite energy signal. In that case, SMT is this, which we can also expand as keeping in mind the energy of the signal. Okay, so what is the energy of the signal for SMT? We can compute the energy as En. So energy of that particular, for the particular symbol, should be integration Sn square t dt. So this integration gives us Am square Eg by 2. So if we take this in mind, the square root of energy is basically the amplitude, that is Sn. So that should be square root of Eg by 2 into Am. So the amplitude of the particular portion of this portion Sn should be this, because energy, the square root of energy is basically the amplitude. So basically the amplitude should be square root of Eg by 2 times Am. So if we plug in this amplitude in this particular relationship, what do we get? So SMT is equal to square root of Eg by 2 Am. But if we introduce square root of Eg by 2, we have to cancel it out, basic algebra. So we do what? Square root of 2 by Eg gt cos 2 pi f naught t, and hence we get our part Sn here and phi here. That is SMT, and this is the very basic idea of pulse amplitude modulation. So from this we can generate our constellation diagram, but we must also specify how Am varies. So Am varies as 2m minus 1 minus capital M for all the symbols possible m, and this is the variation of Am. If we expand this idea for all the symbols, it comes at minus plus 1, minus plus 3, minus plus 5 and all those odd values until minus plus m minus 1. Okay, so now using this idea, we know that SMT is equal to root over Eg by 2 Am. We take an example. The example is m is equal to 2. So k is equal to 1, 2 symbols. What should be the constellation space? Sm is equal to this, not SMT, sorry. So Sm shall be is equal to, for small m is equal to 1, this Am shall compute to be 2 times 1 minus 1 minus 2. So 2 minus 1 minus 2, 2 minus 3 minus 1. So it's a one-dimensional scenario. There is no other dimension. So it's just on the single dimension. So it is minus 1. So Sm will come to be minus square root of Eg by 2. And for m is equal to 2, it is 4 minus 3, that is plus 1. So it should be plus square root of Eg by 2. So this is the constellation space. And now if we draw the constellation diagram, So here it is minus square root of Eg by 2, and here it is plus square root of Eg by 2, and at the middle there is 0 on the axis, and here then there should be the symbol 0, and here there should symbol 1. That's a single case of PAM, 2-PAM, pulse amplitude modulation. Now we can expand this idea. Okay, for a single symbol, the energy is this n square Eg by 2. What happens to the energy for all the symbols in the pulse amplitude modulation? That is average energy. The average energy varies as m square minus 1 by 6 log m times Eg. So the average energy is not same depending on the several values of m. After the pulse amplitude modulation, we have several other mechanisms to discuss. Other is, okay, so we understood that the constellation diagram here is a one-dimensional space. Let's expand to m is equal to 4, 2, 4, 8. What happens in the PAM case? So Sm is equal to square root of Eg by 2 am, and am is equal to 2m minus 1 minus m. Putting m is equal to 4, we get k is equal to 2 bits. So several values of am we get, and those values are 0, minus 1, minus 3, plus 1, plus 3, because we only said am will take odd values by this math. So these are basically multiples of root over Eg by 2, these portions. So it starts at this bit, so it should be here, here, then here, and then here. And it should start at 0, 0, 0, 1, 1, 1, 1, 0. It follows a 1-bit distance between each hop. That means a gray coding fashion. What happens at n is equal to 8, k is equal to 3. We expand further. Minus 5, minus 3, minus 1, 0, 1, 3, 5. So here, 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 here. What happens here? 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. Maybe. Or I missed something. 0, 0, 0, 0, 0, 1, 0, 1, 1. Then I could say 0, 1, 0. Oh, okay. For m is equal to 3, it's okay. Yeah, I missed one support point. So how do we calculate this? Basically, it happens that for m is equal to 1, m has the value 2 minus 1 minus 8. So it should be 2 minus 1 minus 2 minus 9, that is minus 7. Okay, so the support should start at minus 7 and it should go to plus 7. Yeah, in that case we will have here, 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 here. So it should be 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0. 1, 1, 1. Okay. no, I guess 0 1 0, then 1 1 0 is okay. We could do 1 1 1 is okay. Then we could do 1 0 1, and then finally 1 0 0. Okay. So that's how this goes. So this is the scene of 8 PAM. This was the scene of 4 PAM. And this was the, okay, that's it. After the pulse amplitude modulation, we have phase shift keying. So what is phase shift keying? We still expand on that thing, that concept. SMT should be equal to Sn times phi t. But now the Sn is not the same anymore. So we say it is Gt cos 2 pi f naught t plus theta n. So we take a phase shift basically in the phase of the carrier signal. Then what is the variation of theta n? Theta n is 2 pi by m this is the variation of theta, 2 pi by m times m minus 1. Okay, so can m goes from 1 to m, and we have several values of theta m. So theta m should be, when m is equal to 1, theta m should be 0, m is equal to 2, theta m should be 2 pi by m is equal to 3, theta m should be 2 pi by m, and ultimately at the end it should be m minus 1, 2 pi by m. So these are all the possible values of theta m. So we expand on this definition of theta m, 2 pi by m, m minus 1. So we have a situation of phase shifting where we shifting the phase of the carrier signal. So at the end we can expand it like this by using trigonometry. Gt cos 2 pi f naught t cos theta m minus gt sin 2 pi f naught t sin theta m. Now we know that somehow this part, okay, what is the energy of the signal? The energy of the signal En is equal to just Eg by 2. It is the same energy for all the signals. And if it is so, for all the signals, so that it is the same average energy. So it's the same, all over, homogeneous. So the amplitude Sm shall be given the square root of En, that shall be square root of Eg by 2. Is it? No. So we have to introduce the square root of Eg by 2 in this definition. How do we do that? So we do that by doing this. Square root of Eg by 2 times cos theta n. This is our Sm actually. Times square root 2 by Eg cos 2 by f naught t plus square root of Eg by 2 sin theta n times, oh I forgot the gt signal, gt cos 2 pi f naught t square root of 2 by Eg gt sin 2 pi f naught t. Now we can easily see it is composed of two portions. So there is Sm1 and there is Sm2. So it is two-dimensional in its constellation diagram space. So we can say that Sm1 is a set of square root of Eg by 2 cos theta n and square root of Eg by 2 sin theta n, as it is two-dimensional. And we can expand on theta n, which is, okay, we can take square root of Eg by 2 in common. Cos, what is theta n? Theta n is 2 pi by m multiplied with m minus 1, and sine 2 pi by m multiplied with m minus 1. Now this expansion, okay, we take, okay, this is Sm1. Sorry, this is Sn. So this is Sn1 and this is Sn2. What happens is, for every certain value of n, we compute coordinates. And that gives us coordinate points on a 2D axis. So what we are saying is that the 2D axis is something like this on a circle, and those gives us certain coordinates. So the first coordinate shall start from here, here, here in the anti-clockwise fashion, depending on how many m we are considering. Now we can consider only 2 bits. M is equal to 2, that means 1 bit representation. So it will be first symbol here, that is 0, and the second symbol here, that is 1. That is the idea of phase shift keying. Now we are expanding on m is equal to 4, that is k is equal to 3. Sorry, k is equal to 2 bit representation. So there will be 4 symbols. So the first symbol will be here, that is 0, 0. The second symbol will be here, that is 0, 1. Third symbol will be here, that is 1, 1. And the fourth symbol will be here, that is 1, 0. So that is the idea of phase shift keying. And if we expand further, as n is equal to 8, what happens? For n is equal to 8, k is equal to 3. So it should go like this. Here, 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 and here, and here. So it should be something here 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, and so on. So that's how phase shift keying happens. Okay, cool. After the phase shift keying, the next method of digital modulation is quadrature amplitude modulation, that is QAM. Again, we can expand on the same idea. At Snt is equal to Sn times phi t. But now we take a combination, that is Snt is equal to Amc gt cos 2 pi f naught t plus Ams gt sin 2 pi f naught t. So this is a combination of a cosine part and a sine part. Then Amc shall vary between 2m minus 1 minus square root of m, and Ams also varies as 2m minus 1 minus square root of m, and m varies as 1, 2 up to square root of m. Something like this. So we can easily represent as Smt is equal to square root of Eg by 2 Amc times square root of 2 by Eg gt cos part plus Ams times square root of 2 by Eg gt sin part. And then our constellation space will be given by Sm is equal to square root of Eg by 2 Amc and Ams. So that's the idea of quadrature amplitude modulation. And in quadrature amplitude modulation, the energy, okay, I forgot that, the energy of the signal symbol En is equal to Amc square plus Ams square by 2 times Eg. And the average energy of the entire signal shall be n minus 1 by 3 Eg, something like that. So we can see there are two dimensions in the QAM signal also, but it doesn't go like the circular fashion, it's rather goes like in a quadrature manner, square fashion. So how do we draw the cases for QAM? So we have to start at n is equal to 4. Sorry. N is equal to 4, k is equal to 2. It takes values here, here, here and here. And for m is equal to 8, k is equal to 3. 1, 2, 3, 4, 5, 6, 7, 8. Sorry, m is equal to 16. K is equal to 4. 1, 2, 3, 4, 5, 6, 7, 8. Something like this, it goes on. So that's the basic idea of QAM, quadrature amplitude modulation. Okay, after this we understand the ideas of digital modulation, and then we move forward to digital demodulation. That is, okay, all the signals are modulated, waveforms are generated, they are sent through the transmission channel. After they are sent to the transmission channel, what happens? We receive those signals in the receiver side. But do we receive the correct signal? We don't know. We have to estimate a certain message, but how do we know if that message is a correct message or a wrong message? So there is a high chance of estimating a wrong message, so there can be a probability of error. We have to minimize the error probability by a certain decision rule, and the mapper the digital demodulator basically works on a certain decision rule principle, but it can estimate the signal. And how does it happen? Let's look at it further.